Well, good morning. I'm Tony Maggs. I'm a CNRS researcher based in Paris in ESPCI and with a secondary affectation to Paris Sciences et Lettres. My background is somewhat statistical mechanics, and ESPCI is, of course, a lab which is very famed for his historic contributions to soft matter physics. And so when I met Werner Kraut a few years ago, who's a neighbor just slightly up the hill from ESPCI at École Normale, we started talking about how to cross some of his interests, which is irreversible Monte Carlo methods, and some of my interests, which is applications to soft matter physics. And the work that we did, so I should say that I'm rather fraudulent on at least the first half of what I'm going to present, because much of it was actually done by Manon Michel, and so Manon should actually be up here giving this talk and not myself. But otherwise, I've profited a lot from discussions with Tseley, Yang Qin, and Botao Li, who are all students at École Normale in Paris, and we've collaborated on different parts of this project with these people. As I said, soft matter physics, molecular physics, these are major subjects in ESPCI. And I'm going to resume, because since I know that part of the community that's here today is not in molecular simulation, I'm going to maybe resume what you do in standard codes. So, of course, for people who know molecular simulation, this is going to be old hat. But what does one do? Well, this is particle-based simulation, and I put reason to it, a reasonable approximation, and reasonable is that you forget quantum mechanics, and you forget relativity, and you'll forget all the fun things that you learn maybe as an undergraduate in physics, but you keep the fact that atoms and molecules act a bit like particles. They act like classical particles for which you can write down an interaction energy, and he who says, or she who says, interaction energy means forces as well between particles, and then you put this on a computer and you integrate numerically Newton's laws of motion, and there's a lot of papers in material science, engineering, hydrodynamics, biophysics, which will take this basic approach to modeling material properties. And then what you want to do as a simulator is extract configurations, you want to extract energies. Maybe if you're working very, very hard, you will try to integrate energies and get free energies. But the basics of the subject is that you have particles which can have different types of interactions. You can have atoms which have bonds between them, and the bonds are maybe a spring, and so there's oscillations in the length of the spring. But then you have higher order interactions between particles as well. You have, for instance, in this opening here, you have an angle, and in organic chemistry, carbon atoms like to be at very precise angles between each other. So you have some extra bending energy which appears involving this group of three particles. And then even in organic chemistry, you have double bonds which don't like rotating. And so in this case, you can define four-body interactions where there's some torsional angle here, and the rotation on the torsional angle as well can be given some energy. And you have to manage all the interactions and all the forces coming from this sort of energy. And there are various names. You have Lennard-Jones energy, so particles don't like to fall upon one another. So at short ranges, they have some repulsive, I seem to have lost the pointer. There it is. No, it's a little dim sometimes. At short separations, there's a strong repulsion. At large separations between particles, there's some attraction. The angular energies can maybe be a function of the cosine of the angle defining the geometry of a molecule. A problem I worked on, was interested in for a long while, was interactions. Yeah, I don't know whether it also works to advance and to take things. Merci, Bax. Let's. Ah, c'est magique, hein? Ah, c'est fantastique, hein? On va voir, on va voir. Oh là. Maybe we... Which one? This is the thing. Yeah, this is okay. The problem I was very interested in for a long time as well was actually the electrostatic interaction. The electrostatic interaction, if you compare it with the other things I wrote down were rather short-ranged in real space. The electrostatic energy is an energy, the Coulomb energy, which goes as 1 over r, and this can be quite difficult to evaluate in real codes. These are, of course, parametrizations which are very crude, but you know, there are standard groups. There's the AMBER group, the CHARM group, that will give you this year what their best estimation is of the parametrization. Maybe the most recent versions will try to integrate information from quantum simulation and parameterize those by more sophisticated functional forms. These are only validated over limited ranges of conditions. Essentially, you know, if you're simulating water, you know that it boils at 100 and freezes at 0 and has such and such a density and such a dielectric constant, and you try to fiddle around with the microscopic parameters to rather globally reproduce those effects. It gives you limited predictive power when you go outside of the range of data that you parameterize the interactions with. And of course, the evaluation tactics will vary a lot depending on the sort of energy function that you use. For instance, the electrostatic example where you want a sum between all pairs of particles, essentially 1 over r, this you never do in a large-scale code because this loop here takes n squared terms to evaluate. So you do something very different. You say, well, I can write down the Poisson equation, the electrostatic potential, and then the energy, rather than being a double sum, is just essentially the integral of phi times rho over all space. And you know that this Poisson equation is actually easy to solve if you have your charges on a uniform grid. Then you can use FFT. But of course, you're not doing simulations with your molecules on uniform grids. You've got particles like this, which are in the continuum, and then you've got this grid where you want to solve the Poisson equation. And so a major part of the codes that manage, for instance, Coulomb interactions in chemical simulation is this horrible job of interpolation from the continuum to a grid. You solve the Poisson equation, and then you have to push back from the grid to the continuum the forces. And to give you a rough idea, typically 300 or 400, so you push one particle to 300 or 400 sites to reduce the systematic errors that you get. So there's a horrible job of managing systematic errors when you're doing this pushing backwards and forwards. And this can only be done well if you use hundreds of sites for one particle. So there's an enormous overhead. Even if you've gone from an n squared algorithm to an n log n algorithm because you're doing FFTs, there's an enormous amount of work that you've done by this pushing backwards and forwards. And this is sort of an oldish typical example. You put a protein in water, and the protein is sort of this ribbon. And then you surround it with water because proteins in most conditions, above all when you do crystallization, are in solution. And you see here, this is an example with 50,000 particles. And each of these molecules here is water, so every single atom here is charged, and you're doing enormous amount of work with the spectator particles of the water and pushing backwards and forwards the charges to the network every time step. Other examples of what you do, for instance, a very fashionable subject at the moment is ionic liquids. Ionic liquids are small organic molecules. You know, again, imagine that you're describing this by lots of little balls and little angular springs. And these are molecules which are all charged with either positive or negative charges, and you make up solutions of anions and cations. And these are particularly useful at the moment. They're used in green chemistry as a solvent. But above all the high-performance battery technology that you hear about in the modern world are often based on these very stable, very chemically stable objects. So rather than having salt in water solutions, these old batteries when I was a kid, you would put a battery in the toy, and 1 week later there would be a leak, and you would have to throw the toy away. So modern batteries don't use this sort of water-based chemistry anymore. They use things like these ionic liquids. And again, you want to understand the phase behavior, the dynamics of these systems from simulation methods. So just timescales, the molecular dynamics time step is about a femtosecond. One water molecule will rotate in a picosecond, so you have to do 1,000 iterations of your algorithm where every atom is being interpolated to 1,000 grid points, or several hundred grid points. If you're sampling a sodium atom near a surface, and you've got charges around, essentially the equilibration time for the position of the sodium in a reasonable manner is about a nanosecond. Interesting biology is a microsecond to a millisecond. So you need an enormous amount of computing power to do this sort of simulation. And I think we heard from Tony yesterday that was a quarter of the world's computing power goes into doing this, essentially doing this interpolation step. Physicists as well, so sort of stepping back and going to my physicist hat, use often as well very simplified models. You don't have to use all these complicated potentials to answer some questions. If you're interested in phase transitions, water can go from ice to water to steam. That's an example of two phase transitions. The fact that there's a phase transition is not really linked to the fact that you've got these long-range electrostatic interactions. And so often the physicists as well use much simplified models, going down even to sort of billiard balls or hard disks for certain physical situations. Saves a lot of computer time. And then the thermodynamics, of course, does not require knowledge of dynamics. If you're doing batteries, maybe you're very much interested in how the battery is charging and uncharging, so maybe you do need the dynamics. But in other situations, you can replace molecular dynamics by, for instance, Monte Carlo. Okay, ECMC. So I've given you an idea of what you want to do with these particle models. What can you do with ECMC going in this direction? And why would you want to do it? The question is can one find algorithms that are better in some sense than the classical algorithms? That's the real question. And better, there are multiple definitions of better. One, which is fairly easy to determine when you're working numerically, is to take a system which is near equilibrium. And then, for instance, you take water in a fluid phase, and you look at fluctuations in this system, and you look at fluctuations in energy, you look at fluctuations in density, and then you just ask yourself, how long do these fluctuations typically take to decay away? So that's a characteristic time which comes from autocorrelation autocorrelation of observable variables. Another much harder variable to master are mixing times. Mixing times are sort of worst, for me, a physicist, mixing times can be explained as being the worst case situation. If you're for instance, in a system, to take an example, take water, and you stick water at -10 degrees in your fridge. Then you know that it wants to be ice. But you can leave for many hours water at -10 degrees and it stays water. And so the time to go from a bad starting configuration, water at -10, to the true ground state can be fantastically large, hours for grams of water. So this is an example of a mixing time for a physicist, where even if you launch 1 million samples into the fluid, in a crystal, or liquid phase, you will get very, very, if you don't guess the correct down state, which is the crystal, then launching a million simulations into a wrong near fluid state will never tell you about the mixing time. So the mixing times can be very, very difficult. And as a physicist, you have sort of classical examples of things that are very slow to come to equilibrium, or even to get near to the final real state. ECMC, the idea is to break detailed balance, but keep balance. The algorithms today that we use are Monte Carlo, which you just take a particle, you move it randomly. The advantage is the random step can be somewhat bigger than if you're doing molecular dynamics, but you're jumping randomly left and right, so it's rather diffusive. Another nice feature is that you're essentially exact to machine precision, so there are no round-off errors, no integration errors like you do get in molecular dynamics. Whereas if you're doing molecular dynamics and you're integrating Newton's equations of motion, well, then you get some extra very nice things. For instance, you get propagative modes. You know that real solids have sound waves in them, or real liquids have sound waves in them. And so the density fluctuations decay very rapidly. You might have, of course, you have as a disadvantage that you need small time steps for stability. And even though people try multiple time step methods, they're not always very successful. So one would like to keep aspects of both method. You would like to have maybe something which is exact sampling with no integration errors, but you want maybe a propagative mode. And we can see that the ECMC is going to enable us to build algorithms that contain features of both molecular dynamics and Monte Carlo. So again, I'm going to have a different vision of what is slow. So Tony Lelièvre yesterday was talking about, above all, barriers and how to get out of potential wells and so on. And he was saying, well, yes, it's nice to explore well, the bottom of the well, and then we can maybe learn how to jump out of it. So I'm going to be more thinking about, well, what is it that limits the time of exploration in the well? And if you're doing, for instance, simulations of a liquid, then you know you have various local conservation laws, mass, momentum, energy, and that translates into large-scale modes in the system that you have sound waves, you have which propagate at a constant speed, but you have other modes which are slower. Heat, for instance, only diffuses in a quiescent liquid, and there are other modes as well which are slow. The vorticity in a fluid also decays with a diffusive motion. So you have various different modes in the system, and you can characterize them by the exponents. Here I've got omega goes as q squared. Here I've got omega goes as q, and this we call a dynamic exponent z, and which here in the fluid, according to what mode you're looking at, is of z is equal to 1 for the sound waves and z equals 2 for the heat diffusion, for instance. So that the typical autocorrelation time of the macroscopic variable you might look at, say the energy, would be tau, the total simulation time needed would be tau going as L to the Z, with Z the dynamic exponent and L the system size. So of course, molecular dynamics inherits all these modes. If you're doing algorithms, you're not going to escape from what nature gives you from Newton's equations. Though you can cheat a little bit. If you introduce the thermostats, we heard a little bit about ways of thermostating. If you have a thermostat which adds and thermalizes locally, then of course you break local energy conservation and you don't have heat diffusion anymore. The heat diffusion law disappears, but you keep the sound wave if you use a clever thermostat. So as I said yesterday, we heard from Tony Lelièvre many other problems, more local, coming from barrier crossing problems. But here, imagine you're doing a very, very big simulation. If you just want to get the basic state in the bottom of one well correct. The Monte Carlo system, well, essentially, as we said, you're jumping backwards and forwards, and so the density correlation function will typically be a diffusive mode. most large-scale simulations use molecular dynamics and not Monte Carlo. So there were two historic reasons for this. Is that historically the Monte Carlo method did not have a clever ON algorithm or an ON log n. I showed you that people use Fourier transforms typically in molecular dynamics. Now there are, so I even produced myself a Monte Carlo algorithm which is ON. I won't talk about it today, but if you have questions I can talk about it in private. But historically people did not know how to do fast electrostatics with Monte Carlo. And as I said, density relaxes very fast in molecular dynamics. You have sound waves, and when you took your biological molecule 20 years ago or 30 years ago and it was all scrunched up in a horrible local packing, it would expand and relax rather quickly, much faster than in Monte Carlo where the mode would relax by diffusion. So molecular dynamics was historically the major algorithm used in molecular simulation. So event chain. So event chain, as I learned it from Werner Kraut, is that you choose one particle in your system, which you call the active particle, and you move, for instance, this particle here, and you move it forwards until there's an event. The event is here a collision with another particle. And then this particle here moves forwards, so there's a lifting of the dynamic variable from this particle to that particle, and then there's this third particle, fourth particle, and you keep going for a certain total length of path, then you flip directions and you go vertically. This is a rejection-free algorithm. It's clearly just an algorithm for hard spheres. So for instance, with Bernard and Kraut in 2011, and it's clearly not respecting detailed balance because you never go back. And they had tremendous success with this. Oh, what happened? They had tremendous success with this if you look at, for instance, very large systems with millions of particles. And for instance, in the bottom series, you look at essentially coarse grain densities. And you can see as you change the function of, you change the total density of the system, you go from one phase to a mixed phase to another phase, and so you're seeing some sort of first order phase transition with coexistence. And this was an interesting, because the classical Monte Carlo and molecular dynamics codes were not able to see these transitions. So this was an example of something that were able to do in event chain methods, but not in more conventional algorithms. So now we come on to more modern algorithms. How to generalize, and this is more the work of Manon, how to generalize this to hard spheres with, well, not non-hard spheres, but systems with more general potentials, Lennard-Jones angular potentials. And there it becomes more complicated because if you move a particle and you're interacting with several other particles, it's not clear who is at the origin of the rejection, and how do we decide who is at the origin, how do we do the lifting from one particle to another particle. Essentially the solution was found by Manon by using a factorized metropolis rule, so in replacing the standard Monte Carlo metropolis by a probability where you, for instance, if you have an interaction with two particles A and B, then you use a probability of accepting, which is a product of two independent probabilities corresponding to the interaction with A and the interaction with B. This essentially allows you to chop up the rejection and say that another particle is specifically responsible for the rejection, and then use the lifting to that responsible particle. And there were then multi-body, so I gave you the list of all the sorts of potentials that you want. Not only do you need pair potentials, but you want angular, you want multi-body potentials. And this was the solution to this problem. How to do the generalization of this sort of calculation was done by Harland and Manon in 2017. No? Sorry? I've lost the... and it moved 4 or 5 pages forwards. Okay, so the full rule is you sort of split the potentials into disjoint terms. You have an active particle. You have candidate events coming from each of the disjoint terms, and then you select the very first of the events possible, and you transfer the motion to a new particle, which you keep moving in the same direction, and then after a very long trajectory, you flip directions as was done in the original event chain algorithm. And the important point is that this rule here of the factorized metropolis can be turned into essentially an infinitesimal version where the rejection rate is the derivative of the energy with respect to the position, but only if it's positive. And so essentially this is the positivized, it's the force times a theta function. And this was a construction first suggested by Peters and Wirth in another context. So this enables you to do, for instance, fairly efficient calculations with Coulomb potentials. If I have two water molecules, which are two dipoles separated by a large distance, then the force between the two dipoles goes as 1 over r cubed. And so the total rate coming from this derivative is essentially the sum of this 1 over r cubed with all possible other molecules, and you sum that up roughly as an integral, and then you see that the rate of events only increases logarithmically with the system size. And you can actually, by using various tricks, calculate the specific molecule that generated the event very quickly and very efficiently. So without having to use all this complicated technology of back and forward interpolation to a network, you can produce algorithms which are considerably simpler than the classical algorithms for summing up the Coulomb interaction. So now I'm going to flip gears. So this was sort of the big introduction of what you want to do and why ECMC in certain situations can be an interesting thing. But I said, well, hydrodynamics and what is slow, and can we, and those are maybe things we should understand to understand the limitations of an algorithm. So now I'm actually going to go back and make a more detailed presentation, and this is maybe some of the newer work of that I did and Manon didn't do, on the dynamics in 1 and 2 dimensions, so that we can understand what the limits of the algorithm are and whether we can modify the dynamics even further to get to even faster algorithms. So as I said, we want the equivalent of the hydrodynamic description. What are the modes? How do they relax? That characterize the large-scale dynamics of the system to give us more ideas about optimizations. And I'll show you numerical work in 1 and 2 dimensions, but only with the simplest potentials, Leonard-Jones and hard spheres. And I won't be treating these as more useful and exotic potentials that I showed you about. So remember, when you're doing this with an arbitrary potential, we only get events when the potential is moving. So consider first the 1D chain. I put Leonard-Jones particles, one after the other, with some interaction. And the Leonard-Jones interaction is 1 over r to the 12 minus 1 over r to the 6th. Looks like this. And then I imagine, for instance, the green particle is active. And the green particle can be, for instance, here. And if we move to the right, then we can get an event from this little bit here, this rising part of the curve here, or I can have a collision with the hard core on the blue particle, so I can have an event coming from this big rising part of the curve on the right. So now we can see that probably if we have this particle as active, then the most often we get the collision going to the right, but occasionally we generate a few events going to the left. And so the motion of the activity as a function of time will probably go forwards fairly uniformly, and then just occasionally go back a little bit and then go forwards again. So when I started this, I wanted to compare it with Monte Carlo and molecular dynamics, and so I just threw in some Lennard-Jones particles, set them off at high temperature, and I measured the dynamic exponent Z in these systems, and I measured the dynamic exponent Z for density fluctuations in Metropolis, and I got a nice curve which was quadratic, Z equals 2, so there I was very happy. And I did a molecular dynamics simulation, and I see the autocorrelation time going with a Z equals 1, so there I'm happy as well. And then I was fantastically happy because the ECMC, I see, has the same slope. It's parallel to the molecular dynamics code, and I see that it's 2 orders of magnitude faster than the molecular dynamics if I measure in sort of minutes on my computer. So this was a fantastic result for me, and this was at some reasonably high temperature. So then I said, well, what happens at low temperature? And so I redid the simulation at a temperature somewhat lower than the well depth, and then I was extremely disappointed because these 2 curves, ECMC and MD, remain parallel, but they interchange position. So in the end, ECMC has finished up slower than molecular dynamics. So it's sometimes a good idea and sometimes not. So we tried to make an analysis of why things were slowing down at low temperatures. And we made the following remark, that essentially at very low temperatures, things look like they're locally quadratic potentials. And we've got the position of the particle, xi, and then we've got some mean position, L, which is between the particles. And we also make the remark that the sum over all particles of this thing here can be written as well as essentially the displacement of the xi's plus a constant. And this is true because the xi minus 1 minus xi is essentially a perfect differential. So we can take out linear terms in this sum and throw them away. They just turn into a constant. But when we do the algorithm at low temperatures, the events are essentially dominated by this cross term, the linear term between L and this difference here. So the thing that's slowing you down is this sort of spurious linear term because you've not got your particles at their equilibrium separation. So we said, well, we must be able to do better by removing a linear term. So we add to the energy that we introduce into the event rates an extra linear term in each of the coordinates, but which just sums to a constant. And so the potentials now get essentially turned, rotated. So rather than having the normal Lennard-Jones, we have a potential which has a much stronger rising part here and a similar descending part here. And then we choose from the arguments that we had on the previous transparency, we worked out that at 0 temperature, the optimum value of the value of the field to subtract was the force between the particles. And the obvious generalization of the force between the particles at finite temperature is the pressure. And so we chose that we impose that the value of this h in the prefactor is an approximation to the pressure. And so we redid our simulations, and the result was quite magical. We have the slope 2 from Metropolis. We have the slope, I didn't do the normal Monte Carlo, but this is the one that we should look at. This is the ECMC without restarts. And if we look at the slope here, we have a slope of 1/2. We've produced a dynamical system with a dynamic exponent 1/2, so that the relaxation time of a system only increases as the square root of the physical dimension. And before we had something which is linear. So not only have we sort of accelerated by a factor, we've changed the scaling of the dynamics with the system size. And so the bigger we go, the more we win. So we've accelerated considerably the dynamics, and even more surprising, we've changed the dynamic exponent, and now we have an algorithm that is relaxing faster than molecular dynamics. And then we look at for instance, since we have these, essentially we have balanced, oh, it's not going back. Since we had this Lennard-Jones, which was rotated, essentially we have balanced events going forwards and backwards. So it goes backwards and forwards equally often. And you might think, well, the large-scale motion must be diffusive. Thinking. It's not. I think there it is. And so actually, when you look at the motion of the activity is hyperdiffusive. You get some strange law that the motion of the activity, the typical motion is t to the 2/3. This was why this is the one that is not liking to display. And the other thing you can look at is, for instance, returns to origin, which also include an exponent, for instance, 1/3. So you've generated some very strange stochastic process for the motion of the activity in the system, and you look at the motion, the way one given particle advances, it advances as t to the 1/3, for instance. So the question is why there's this very strange stochastic process, and what is the continuum description of this? I started out by talking about hydrodynamics and macroscopic observables in a fluid, and now I've ended up with some very strange stochastic process for the motion of particles and the motion of activity, with exponents that I don't really know how to explain. The thing I can say is that you can do a bit of scaling, and these exponents of 2/3 and 1/3 that pop up in the motion of the activity are the ones that are consistent with a dynamic exponent z of 1/2. So how can you do this construction? When we did it originally, so it was cooked up to remove this sort of drift term, this constant term in the interaction between two particles in Lennard-Jones. And it looked very, very specific to one dimension. Is there a way of building a similar thing in 2 dimensions? And the answer is yes, 2 or more dimensions. And what we do is the following. So this, I give an example of a system of hard spheres. We take our system of spheres, and over the spheres, we overlay a system of lanes, and the lanes are slightly narrower than the size of the particles. Then we do exactly the same thing as in 1 dimension. We now consider within a lane, everything is linked with this extra factor field potential. So for instance, between A and B and C, and then wrapping around from D to A, we add a linear potential. But between B and C, we don't add a linear potential. Even though B and C are close, their centers are in different lanes, and so we don't add this extra linear potential. So now when we look at the dynamics, we can look at, for instance, if B is the active particle, then there are 2 things that can happen. B can either have a direct collision with C, and you get the lifting from B to C, and the activity changes a lane, or you can have the back lifting. You go from B to A, coming from the extra linear potential. And again, we choose the strength of this extra linear potential to be what you can look up as is the potential, the pressure at the density that we're simulating at. First thing to do, so this is starting to be a little bit exotic in terms of construction, and we didn't believe it straight away. But you can do various statistical tests. You do the simulation using a classical algorithm, and then you use the event chain with this extra factor field, and you do 2 series of simulations, and you look at, for instance, the radial distribution function, and you look at this in a cumulative manner. For instance, there are no particles less than at a separation less than 2 sigma. and then you look at the number of particles between 2 sigma and twice 2 sigma. And so this gives you some curve of, which is the integral of the radial distribution function. Then you take 2 simulations and you look at the distance, the vertical distance between those two curves. This is clearly inspired by the Kolmogorov-Smirnov's test, but it's not quite that because the samples are not entirely independent. But you see that as the number of samples, you do longer and longer simulations, and here we take, for instance, 4,000 particles and 1,000 recordings, and as we plot the vertical distance between the two curves as a function of the number of recordings, it decreases as the square root of the number of recordings. So at least and at the end, our Kolmogorov test is taking 2 days to run, since we have a rather large number of recordings. So at least in the numerical accuracy of the data, we seem to be converging to the same, for instance, radial distribution function, which seems to be implying that the algorithm is correct. Then we looked at the speed, and we look, for instance, if we took at the Bernard-Kraut algorithm, which is the event chain without this factor field, then the autocorrelation time for the density are essentially these red dots. And we see that there's a line which corresponds to z equals 1. So the classical event chain algorithm is still giving you a dynamic exponent of 1. Whereas now you look at the blue points, which is the simulation that I do with this extra factor field. And then I can see that essentially the speed of the algorithm measured in sweeps is independent of the system size. So I've gone down all the way to a dynamic exponent z equals 0. It might be a log. There's an argument in the XY model in Zerlé's thesis that says that this should be a log. Yes? So this is not, so this is in the fluid. So I'm not doing phase transitions. I'm trying to do algorithms that are good enough to, for instance, equilibrate water away from a phase transition. I'll say a little bit about phase transitions at the very, very end. So for me, what we're looking for is a way of simulating water much faster, so that when you can do what Tony Lievre was doing yesterday, you're equilibrating much faster in your little basin of attraction, and then you can jump out much farther. So what I'm looking for is rather algorithms that are away from the critical point, but give you better dynamical exponents, because you're sort of cutting off the hydrodynamics and you're cutting off other. So at least in that point, it's a success. And you can look at the trajectories that are generated now by the algorithm, and you look at the activity. So you've got your active particle, and so you can be jumping backwards and forwards. If we can go, so for instance, you can have the activity which jumps back here, or it can jump forwards and then hit C, and the lane changes. And so in the end, you generate what seems to be a large-scale diffusive motion of the activity. So this is very different from the typical trajectories that you see in normal event chain simulations, where you get a bullet going straight through the box. So now you've replaced the event chain, the activity bullet, which sort of bounces off everything, into some diffusive motion, but at every moment the particle is moving forwards in the same direction. Yeah, that works even less well. It worked. So we did some work as well, just looking at the modes that are generated by the algorithm. What if you look at your system and you for instance create the matrix of cross correlations of motion of a particle, and then you diagonalize that matrix, then you get a load of mode structures. The highest amplitude modes look like shear modes. So, for instance, a particle is moving. You've got the algorithm which is pushing you forwards, and then essentially the lowest and highest, the highest amplitude fluctuations are shear motions like these, Then you've got essentially a longitudinal mode, which is the fourth mode up, so you can look at the mode structure. And then when you've got the mode structure, you can look at how each mode relaxes. And if I take, for instance, the Bernard-Kraut algorithm, and I use very long trajectories, this was something that they realized that if you take very long trajectories, it doesn't work so well. Very long trajectories before changing direction in the algorithm. What goes wrong is that you get in the longitudinal modes, for instance, this is a longitudinal mode, the motion is here horizontal, and these bands, this is +1 and this is -1, so there's sort of a scrunching going on longitudinally. This longitudinal mode goes sort of oscillatory if you use a very long, trajectories, whereas if you use very short trajectories in the Bernard-Kraut algorithm, then you get rid of the oscillation, but the transverse mode becomes slow. We use our algorithm, and essentially every single mode relaxes at the same rate. And you see the timescales are completely different here. This is a system of 128 cubed. Here the autocorrelation times are sort of 100 on this scale here. Here the autocorrelation times are 2 or 3. So the algorithm essentially relaxes every mode simultaneously. Conclusions. We have so event-driven frameworks can be interesting as an intermediate step between Monte Carlo and molecular dynamics. Without the event chains, you get Z equals 1, which is a bit like molecular dynamics. The densities relax fast. The factor field opens lots of questions because I don't know how to describe the macroscopic dynamics of the system. And if there are any people who are capable of writing down a Fokker-Planck equation that gives me the right exponents of 1/3 and 2/3, I would be very interested. There are fairly obvious generalizations. You could do multiple Walkers at the same time, multiple active particles at the same time. So this is interesting if you want to parallelize. The method is open to use of general potentials that you need in molecular simulation. Some things work extremely well. For instance, the density equilibration, which I showed you. Some things don't, and that's the question of what happens when you go to the hexatic phase transition in this 2D system. Well, the rotational degrees of freedom don't go any faster. In fact, they go a little bit slower. So even though we've got something that is working very well in the fluid phase, it's not given us a win in the hexatic phase. So we're still, that's our next project is how to go further, how to couple better the rotational degrees of freedom that are interesting, both in hard sphere systems, but also in water. You want to be able to spin your water molecules maybe very quickly. And as I said, anyone who has any ideas about the hydrodynamic description of this sort of system, I would be very interested. And I finished, and maybe I'm on time. Yes.
I was asking about the hydrodynamic limit at the end because it reminds me, at least in 1D, of these asymmetric exclusion processes for which there are actually hydrodynamic limits.
So I think Werner did some work maybe with Soleil, where indeed they made the remark that there were similarities and managed to calculate the mixing time in 1D, for instance, without the factor field.
A bit technical.
Yes.
So when you're in 2D,
yes.
Do you have some kind of extra refreshment on top of your factor fields?
No, there's no. So there's no extra. No. Of course, the factor field adds a lot of randomness compared to the standard. For instance, in 1D, if you do. If you don't renew your chain in 1D, then essentially you end up with a periodic system. Whereas the most efficient version of the factor field in 1D has no refreshment. If you have refreshment, it slows it down.
Look at this later.
Mm-hmm. Oh, it's very possible. But the magic, but the thing that's really magic for me is that you decrease the dynamic exponent. That was, for me, I was expecting to diminish the prefactor, but that you can play on the dynamic exponent of the system and relax asymptotically faster the bigger your system is still to some degree magic for me. That you go from z equals 1 to z equals 1/2 in 1D and 0 in 2D.
One last question. So, because you have this jellyfish package, and I see you are working with them on that, right?
Yes.
That's the multi-threaded, that's the jellyfish package.
So that's the second paper. Yes.
Second, yeah. So what can we do with the jellyfish package now, actually?
Sorry, what?
What can you do with
So
the jellyfish?
the jellyfish package is a Python program that essentially implements everything that's in this JChem Phys paper. And for instance, does I showed you a little bit this you could take dipoles and get a rate which was 1/r³, and so that the thing only slowed down logarithmically with time. So that implements, for instance, that algorithm. As you can see, the algorithm fully implemented, and it even has test data. So we have classical Monte Carlo compared to the Python implementation, and you can check to whatever precision that you want that everything works. So it essentially implements all the Coulomb algorithms that we had, and goes as far as simulating a few water molecules. So it is a full implementation of how you would, for instance, calculate the dynamics of water molecules. And it's on GitHub. So the point is that you can download it and read the code.